Okay, thinking back to third year physics when we did electricity 1 and 2, and we talked about the effective voltage of something. Okay, so that means basically something could have an AC voltage, so it could have a peak voltage of higher than the effective voltage, but if you average it out, and we kind of just said average it out, you get a certain voltage that's slightly lower than the peak voltage, or it's about 0.7 times the peak voltage, and that's the voltage that it gives out really after everything's been averaged out. Okay, so what we said averaged out when we were talking about it in National 5, it's actually a special type of, it's not really an average, but it's a special type of data manipulation, which is kind of like an averaging something, but it's called root mean squaring of something. Okay, so mains voltage, we say mains voltage is 230 volts because that's what it gives out sort of on average, but it doesn't actually give out 230 volts consistently. Because mains voltage is AC, it's got a sinusoidal waveform, sort of like this diagram here. Okay, so we've got sinusoidal waveform, so basically wibbly wobbly wave. Okay, and sometimes it's at 230 volts. Let's put 230 there. And sometimes it might be at its peak, which is about 325 volts. Okay, so that's the peak. And 230 volts is somewhere around there. Okay, so it's about 0.7 times peak, which is 325. Okay, so the peak of that AC would always be 325. But we've got what we call root mean squared value. That is the value that it actually gives out, taking into account the pluses and the minuses of everything. So the effective voltage, or the root mean squared voltage, we've been calling it effective, and you can still call it effective. Effective voltage is 230 volts. But there are times when it will give out more than that, and times when it'll give out less than that, but it's sort of averaged out. So the voltage cannot be represented by the mean value because the mean value is 0. So we said it's kind of averaged out, but if you had 325 plus minus 325, the average of that would be 0. And nor can it be represented by the peak value because it only reaches its peak value twice in one wave, so twice per cycle. So that 230 volts is known as the root mean squared voltage, RMS voltage for short, because nobody has time to say root mean squared every time, whereas the RMS stands for root mean squared. So the definition, a 230 volts RMS AC supply has the same heating effect as a 230 volts DC when connected across a resistive load. So basically what it means is if you connected a resistor to a 230 volts RMS AC supply, it would give out, it would be maybe give out the same heat, so maybe 10 degrees C, as, I'm just making that value up by the way, as if you plugged it into a battery which was the same voltage, 230 volts. Okay, same with a light bulb. Okay, which might be a little bit easier to visualize. If you plugged a light bulb into 230 volts RMS supply, it would be the same brightness as if you plugged it into a 230 volt DC supply. But we know that DC doesn't change, it just stays at that one value. But the 230 volt RMS supply will be above and below at some points. But its overall use, its overall effective is it gives out the same brightness as a 230 volt DC supply. So examples of resistive loads are the element of an electric kettle or the filament of a light bulb. So there's an experiment that I'm going to show you a video of. So what this experiment is it's a lamp, and you can either connect it using this switch here. You can either connect the switch to A, which means the lamp is connected to the AC supply, or you could connect it to B, which means the lamp will then be connected to the DC supply. Okay, so this is our AC, and this is our DC supply. So that would be a cell, or an AC would be the mains voltage, or a power pack that provides AC. We've also got a variable resistor there in with the DC supply. So depending on which way round that switch is connected, the lamp will either be connected to an AC supply or a DC supply. The lamp has also got an oscilloscope attached to it, just so we can or are able to see the peak voltage of it. So the first thing that you would do, and I'm going to give you demo results here, but the video might give you slightly different results. If you connected switch to position A, you've got your AC supply across the lamp, and you measure the peak voltage across the lamp by looking at the oscilloscope. And the peak voltage, when I did this last time, was 10 volts. Okay, so that was the peak voltage read from the oscilloscope, because obviously you can't read the peak voltage from a meter because it would only give you the RMS value. Then you move the switch to port B, so then it's connected to a DC supply. Okay, but before you do that, you need to place a light meter close to the lamp and note the light intensity of the reading. Okay, so that light intensity you want to be the same throughout this experiment. So you've got a light intensity with 10 volts as a peak voltage. Then move the switch to position B, so it's connected across the DC, and adjust the rheostat, the variable resistor, until the brightness gives the same brightness again. And then you measure the DC voltage of that DC supply, and it comes to about 7 volts. So where the peak voltage was 10 volts, that same brightness was equivalent to the DC supply of 7 volts. And actually the ratio of this is, and where we said it's about 0.7 volts, the ratio is RMS voltage divided by peak voltage is 1 over root 2, which is the same. You can have the same ratio as RMS current over RMS voltage, over peak voltage, peak current even. So if you rearrange that, you could say that the peak voltage, V peak, equals root 2 times by the RMS voltage, or the RMS voltage is the peak voltage divided by root 2.